Hi, and welcome to the Foundations course Lesson 8, Thoroughly Designing a Study Part D on Prognostic Research. As usual, we will start with an overview of prognostic research, focusing on the data collection and data analysis process. The aim of prognostic research is to determine the ability of a set of variables to predict an outcome. And as a typical study design, a prospective or retrospective cohort study is used to eventually study disease occurrence measures or survival as outcome measures, and the analysis type usually includes multivariable regression modeling with models like logistic regression resulting in odds ratios, Cox proportional hazards models resulting in hazards ratios, and less oftenly Poisson regression models resulting in rate ratios. You should use the STROBE criteria since prognostic research is observational research, but in addition you should also follow the tripod guidelines on prediction models for individual diagnosis and prognosis. Now let's start by putting prognosis into the right research context. Without prognostication, this would be the situation. So we start with signs and symptoms for a certain patient, and then diagnostic tests are performed, and based on the clinical decision-making process, we judge whether a patient is likely to have the disease or not have the disease, and thus receive therapy or no therapy. And we can only use this information on a group level to predict a certain outcome for patients that are diseased and undergo therapy, or that are not diseased and don't receive the therapy. And since we would only be able to predict average outcomes for groups, we would manage all patients similarly. But with prognostication, we can change this. We still have the same clinical process of signs and symptoms, diagnostic tests, and then therapy or no therapy. But we can now use information from all of these phases to build a clinical prediction model that allows us to predict the outcome for all individual patients. And that means that we can tailor our therapy to the individual patient. So for example, patients with a poor outcome, as predicted by the clinical prediction model, may require more aggressive treatment, or maybe no treatment at all if that treatment would be futile and very toxic. Now, before we move on, let's make sure that we know what we're talking about when we refer to a statistical model. This definition is already discussed. It's an explanation of a dependent variable by a mathematical function of explanatory variables. But remember that there are two different purposes of a model. And in prognostic research, we are mostly interested in clinical prediction models where the model is the goal that allows other researchers to accurately predict outcome in their individual patients. So this is what we will focus on. And let's start with the traditional approach to diagnostic research. Usually researchers want to know, can a determinant predict outcome in a study domain? And they use a retrospective cohort study to do that. In the data collection, patients are selected that are potentially at risk of developing the outcome of interest, starting from selecting those that develop the outcome and working backwards to the common pool. And then a retrospective electronic patient chart review is performed to collect the determinants of interest and other baseline characteristics. In the data analysis, oftentimes no sample size calculation is performed, missing data are simply ignored, and variables of interest are selected from the database based on significant associations with the outcome in a univariable analysis, upon which they are entered in a multivariable regression model. And the thing that researchers focus most on is to evaluate whether a statistically significant relationship can be established between the determinant and outcome of interest in one of multiple tested multivariable models, of which only the best will eventually be reported in the research reports. And in the conclusion, in the case of no significant relationship, it is claimed that the determinants are not independent predictors for the outcome. And in the case of a significant relationship, they might claim something like, we have developed a normogram based on the determinants that can be used for prediction of the outcome. Now, as you might guess, there are several things here that I think should be done differently. Let's look at the GCR approach. The first principle is to know your type of prognostic research. Are you exploring new prognostic factors, or are you trying to replicate those explorations in external validation studies? And sometimes replication studies fail to replicate the findings of the exploratory studies, and then we should go back to the drawing board and see if there's a real signal in the proposed prognostic factors. But let's assume that they can be confirmed. Then eventually other studies need to replicate these findings as well and update the strength of the association. This process is called recalibration, and it changes the regression coefficients in externally validated cohorts until the model is clinically accepted. Now, there's a very useful framework for the phases of prognostic research, and this is called the Prognostic Research Strategy, published in the British Medical Journal. And it describes that type 1 research, fundamental prognostic research that provides new prognostic information, and it usually entails descriptive research in which an outcome frequency is assessed, typically in a group for which there is limited clinical data. In the second type, we look at prognostic factor research, and it can uncover or confirm new predictors. And these are prognostic studies in which the prognostic value of a factor with unknown significance is explored. Now, the third type is that of prognostic clinical prediction research, where a multivariable model is built to predict the risk of a specific endpoint for individual patients, and after internal and external validation, a normogram can be made. So this helps clinicians estimate individual prognosis. And in the fourth and last type is that of stratified medicine research, of which the goal is to identify patients who will have the most clinical benefit or least harm from a specific treatment. So this evaluates the clinical impact of the introduction of a clinical prediction model. And as you can see, this has striking similarities with the research types of diagnostic research. But for example, the stratified medicine research is the prognostic counterpart to the diagnostic clinical utility studies. And the similarity between prognostic and diagnostic research is pretty illogical, since both diagnostic and prognostic research are prediction research that only differs because of the influence of time in prognostic research. Now, the second principle of the GCR approach is to spend most of your time on the study design process and aim for a sufficiently large cohort with high quality data that is representative of the study population. And you should refrain from data digging without a pre-specified analysis plan in a small retrospective cohort. Unfortunately, this is very, very common. You should also refrain from looking for importance based on the data analysis itself, and refrain from building multiple models and only report those with significant findings. Why? Well, you might score a nice publication, but you will not impact or improve clinical practice. And the reason for this is that the significant associations that you have measured in your data are most likely the result of a overfitted model in a non-random sample that is not representative of the population. And thus the problem here is not that of confounding as in, for example, intervention research. But the problem is that although your fitted model might be able to predict outcome in your cohort, but it will not be able to predict outcome in other larger cohorts that are more representative of the population. And thus, critical thinkers will not take your research seriously. And the problem here is that it will put you into the waste quadrant of no relevance to advancing knowledge and no clinical applicability. And therefore, you realistically have no chance of impacting or improving clinical practice. But you do contribute to the mass confusion that is a result of the massive amount of so-called prediction research that is published but not replicable. And so instead, we should play the long game. Design a valuable cohort study if retrospective. Make sure that it's sufficiently large and contains high quality data. Base your data analysis on clinical importance and use a pre-specified modeling plan and report all models developed. It might require a little bit more preparation, but you at least have the chance to impact or improve clinical practice, and you will definitely benefit from it in future endeavors. Then the question arises, how do we get a large, high-quality data cohort? The most important factor is to standardize your data collection. You could, for example, design a prospective cohort study and use a multi-center database registry study format to do that. And this could mean that you collaborate with other hospitals or health organizations, etc. And try to use hard outcomes instead of proxy variables. But what is large enough? Well, that's a question of sample size estimation. And the problem here is that insufficient sample size leads to an unstable model, overfitting, which is too extreme regression coefficients, and an inability to generalize findings to the target population. And there's a rule of 10 as a rule of thumb, that the bare minimum for the development of a multivariable model is 10 events per variable in the model. Remember, in logistic regression, this is the smallest category, so either events or non-events. But in general, the sample size should be at least a few hundred, if not 1,000 patients. And consider sharing your study plan before starting the study. And you can do this through a registration in a study base on, for example, clinicaltrials.gov or isrctn.com. Or you can publish a study protocol. And this really creates accountability for yourself, but also increases transparency for others. And it will increase your chances of being able to publish your article in a good medical journal. Now, the third principle of the GCR approach is to predict potential sources of bias and think of ways to avoid them. And we have discussed all of these bias types in detail in the other lessons, so I won't pay as much attention to it now. But selection bias can be a problem in prognostic research, with the biggest problem being that the sample is not random, so you should think about a good source for recruiting target patients, record patient characteristics of all eligible patients, and also record reasons for dropout or loss to follow-up. And maybe the biggest problem is that of information bias, and of course you should train the data collector, standardize the data collection, and if possible, blind the outcome assessor to prevent observer bias. And as previously stated, confounding is not an issue in prognostic studies, but effect modification or interaction is. And the fourth principle is to understand nuances of prognostic research concepts and terminology. We start with a clinical problem. From this, we construct a research question and study design. And in prognostic study, we measure several variables that might be of interest as predictors. And so we use them as input to our multivariable clinical prediction model. The goal of the prediction model is to accurately predict a certain outcome of interest. And thus, in a sense, the outcome of interest is some kind of output of the clinical prediction model. But we also use it as an input to construct the model equation. And the discordance between the predicted and observed events is reflected by the residuals. And if there is a large discordance, then it is said that the calibration of the model is poor. And what we know from experience is that the prediction model tends to fit too well onto the data, and it is said to be overfitted. And therefore we need some kind of correction, which we call the internal validation. But eventually we need to externally validate the model to see if it also performs well in other cohorts. And we do that in replication studies, where the data of these external cohorts are used to update the multivariable clinical prediction model along with its equation, with the same goal to predict the outcome of interest. And after external validation and model updating, we have increased the generalizability of the model, which means that we can use it in the population to inform us about our clinical problem. That's the basic process for building and validating a prognostic model. Now let's zoom in on the first part of the process, the part where we select variables as input to the clinical prediction model. And these variables are candidate predictors or prognostic factors, biomarkers. You should choose the input variables for your model on the basis of prior studies, biological medical knowledge and reasoning, and exploratory graphic analysis. And I think you should refrain from using univariable analysis significance as a selection criterion. And remember that basic patient characteristics like gender, age, and medical history tend to be really strong predictors, and thus should always be considered as variables for the model. Do not categorize continuous variables, since this decreases power, and try not to choose variables that contain the same or similar information, since this creates a problem that is called multicollinearity, and it destabilizes your model. With regard to categorical variables, it is wise to use a logical reference category, so think ahead of what you want to show with your results. Do you want to show a negative or a positive predictor? And for continuous variables, use a logical scale. So for example, age in years, not in months, or laboratory values in standard parameters. Now, with regard to the output part of the outcomes of interest, you should choose a meaningful outcome that you have measured in your cohort. And common outcomes are overall survival, adverse event rates, and quality of life. But try to avoid proxy variables unless they are clinically meaningful. Choose time to event outcomes, for example overall survival, over event rates at a fixed time point, such as a 1-year survival rate, unless the event rate is clinically meaningful, since you're throwing away precious information. We haven't discussed it in this course since it's a more advanced type of analysis, but clustered and longitudinal data require special analyses. Now, on the prediction side of the process, there are several things to mention. Let's start with some definitions. The meaning of a prediction model is a bridge between predictor variables and the outcome of interest in the form of a statistical equation, with the goal being here to obtain the simplest model that can predict the outcome best. And calibration is the concordance of observed event frequency and predicted event probability. Discrimination is the model's ability to distinguish patients with an event from those that are event-free. Internal validation is the procedure to correct for optimism and overfitting. And external validation is model testing and updating in a different study population. Now here's the GCR modeling strategy that I would advise when developing a new clinical prediction model. Start with a full model of interesting candidate predictors. then check model assumptions, transpose variables if necessary, or include time factors in the case of Cox proportional hazards regression with violation of the proportional hazards assumption. Subsequently, try to reduce the model one variable at a time, starting with the least contributing variable. Compare the reduced model with the prior model on the basis of the Ikaikis information criterion value, and stop reducing the model at a difference in AIC value of equal to or less than 2, because this means that the further reduction, which would lead to increased simplicity, does not weigh up against the loss of predictive ability. Remember that the Ikaikis information criterion is a combination of predictive ability and a penalty for the number of predictors in the model. Now also compare this last model and the prior reduced model pair with a likelihood ratio test and confirm a significant result, since this means that the models are not equally predictive and the fuller model is a better predictor. Once again, check model assumptions for potential violations with the final model and evaluate calibration with a calibration plot and discrimination with a C-index or area under the curve or R-squared value, and then perform internal validation. I would advise using a bootstrap method to determine a shrinkage factor for the regression coefficients, update them with that shrinkage factor, and then update the discrimination values and report all characteristics of the model build and state the final model equation. Now this is a calibration plot where we plot the predicted probability against the observed probability. And the diagonal line is a perfect correlation between the two. Now, that is hardly ever achieved, but the point is to check whether there are large deviations from that line over the range of predicted probabilities. And for this example, that's not the case. So for both of these lines, calibration is good. But let's just say, for the purposes of explaining a point, that this line is an example of a less than optimal calibration, where in the lower predicted probability range, the model predicts a higher probability than observed, and in the higher range, the model predicts a lower probability than observed. Now, after internal validation and applying a shrinkage factor to the regression coefficient, this black line represents the bias-corrected model, and you can see that the calibration is a little bit better. It's closer to the diagonal line, especially in this range of predicted probabilities. And note that some people promote the use of statistical evaluation of calibration with something like the Hosmer-Liemshout test, but I prefer a graphical assessment. Now, discrimination can be assessed with the C-index, which is equal to the area under the curve, and it represents the percentage correctly classified, with perfect being 1.0 and the worst achievable number is 0.5, or with R-squared, the percentage of variability explained, and the range is from perfect 1.0 to worst 0.0. Now, in validation, we've already discussed internal validation, which is performed in the initial study, where we use the final model to correct for overfitting or optimism using a bootstrap method. This will result in a shrinkage factor. We apply that to the regression coefficients to obtain the final model equation with less extreme regression coefficients. External validation is performed in replication studies, where we use the model equation of this final model, but we recalibrate it, update it, and check discrimination again, and then we come up with an updated final model that is externally validated. And there's a term here which is called transportability, which refers to the ability of the final model to hold up to changing circumstances. And this can be temporal, whether a model is fit to stand the test of time, but it can also refer to a geographical distribution, whether the final model is generalizable to various study populations across the world. Now, the fifth principle of the GCR approach to prognostic research is to report the final model equation. This is an absolute must, in my opinion, because it allows other researchers to work with your model and perform updating, recalibration, etc. You've already seen all of these equations, so I'm not going to discuss them again, but remember that the linear regression model is the simplest equation, and we use a link function in logistic regression, Poisson regression, and the Cox proportional hazards regression models. Now, for this last model, it's a little bit harder to define a final model equation, since we cannot easily define the baseline hazard at time point t, but the main output is the hazard ratio at time point t, which is constant over time. But what we can do is center the model equation around the mean variable values and then estimate the baseline survival rate at time point t for various t values. So for example, 1 year, 5 years, 10 years, etc. And the sixth principle is to consider clinically useful prediction rules. So this refers to the way that you present your study results once a model has been internally and externally validated. And I can recommend you this paper in the British Medical Journal that discusses the various possibilities in detail. And the basic idea here is that you want to develop a figure or another sort of tool that lets the clinician intuitively calculate a probability of outcome on the basis of their individual patients' values to the variables in the prediction model. And to do this, you need to award certain weight to the values in the variables based on the regression coefficients. And this is, for example, a simple point score system that you might have seen before, where continuous variables are broken up into common categories, for example, age over here, and then there are certain categorical variables as well, cirrhosis, yes or no, and patients get a number of points per category. And here you could see, for example, that the reference category in age is 55 to 64, which is probably centered around the mean in the cohort. But patients older than that get 1 point, and patients younger than that get points subtracted. And patients that have cirrhosis, for example, get 3 points, whereas no cirrhosis is the reference category. And then you can add up all the points to the values that are applicable to your individual patient and look up the total number of points in the system, and that number needs to be related to the probability of the outcome. And in this example, that's probability of death at 1 year and probability of death at 3 years. Now, a more graphically appealing way of doing this is using a graphical score chart, which is very commonly used, for example, in cardiovascular risk scores, where the chart is constructed in a way that it is broken up into different rows and columns that correspond to values in the model variables. And this is based on the same model as the point score system that you saw before. But for example, over here you can choose the age of the patient, whether the patient has cirrhosis, yes or no, and then we need to look up the corresponding column, depending on whether the patient has cholestasis, yes or no, and then we need to look up the albumin level to find the right box for the patient. And the benefit here is that you can work with colors and exact numbers. So, for example, we can read off in this box that the probability of death at 1 year is 0.03, but we can intuitively see that it is yellow. So that means that it falls in the low risk category of probability of death at 1 year between 0 and 0.1. Whereas these are more the risk categories that are high risk, and the green and the blue ones are in between. The downside of this is that you can only choose one outcome, or for example here, probability of death at 1 year. And if you want to also let the clinician calculate the probability of death at 3 years, you need to make an entire new score chart. The nomogram is also a graphical display of the prediction rule, where here on top we see the number of points that can be awarded for each variable, ranging from 0 to 100. And then per variable we need to read off the number of points on this ruler. So for example, a patient with age 50 gets 20 points for his or her age, and someone with cirrhosis gets around 40 points. And we do this for all the variables and then add up the number of points to get the total number of points. And for example, if we say we end up with a total of 160 points, we can read off the outcomes in these rulers below and see that a patient has a 0.2 1 year probability of death and a 0.58 probability of death at 3 years. While it can be practical, I think this is one of the least intuitive presentations of your prediction rule, and it's a pretty imprecise method due to errors made during the read-off process. And then the most modern way, and I think the best way to present your prediction rule, is to use a website or an app that just calculates the exact outcome probability on the basis of the model equation. But obviously this is the most labor intensive way of creating a prediction rule, but I think it also increases the chance of integration into clinical practice in comparison to the former ways of presenting your prediction rule. Well, that's it for prognostic research, and I hope you're ready for the next stop, which will be intervention research.